Greetings everybody, and in this ring theory video we're going to be taking a look at subrings, and we're also going to be introducing ring homomorphisms. So let's start off with the definition of a subring. Let R be a ring, then a subset, S in your ring R, is called a subring if the following four conditions are met. First of all, you need closure under addition, which means if you take two elements in that subset S, it must be that their sum also lies in S. You also need to be able to find each element's additive inverse inside of S as well. Multiplication must also be closed inside of this subset. And finally, remember rings need to have a multiplicative identity. That's one of the axioms we're assuming for this series. So you need the elements of 1 inside of S. And notice we're requiring that the multiplicative identity is inside of the ring S, but not the additive identity. And the reason why is because, well, the additive identity is already in there. Because if you have an element A in your subset S, then negative A must be in that subset as well. But their sum must also be in S, so A plus negative A is 0, so that forces the additive identity 0 to always be in S. So this is quite nice over here, because if you have a subset of ring R, you don't have to go through all of the ring axioms again to verify that it's a ring. You can just check these conditions over here. Just a nice remark I want to make. Conditions 1 and 2 are actually equivalent to requiring that for all A, B in your subset S, it holds that A minus B is also in your subset S. So to see this, first of all, notice that 0 must be in S, because if you just take the same elements, you subtract it, you get 0, so 0 is in S. But now if you take A to be 0, then this forces the negative of B to also be in S, which is the second condition. And once the negative of all elements is inside of S, then if you just replace B with its negative, then you have A plus B, which gives you back the first condition. So if you really want to, you can just replace that condition with the first two over here, and there's only 3 conditions left to check. So maybe let's give some examples of this. We have the ring Z, and this lives inside of the ring Q. This lives inside of the ring of real numbers, and this lives inside the ring of complex numbers. Actually, these are fields, but we're thinking about these guys as rings at the moment, just so we can have an example of a subring. I've also given you some examples when we took a look at polynomials. If you have the ring R, this is a subring of the polynomials, but this is also a subring if you take two elements and you adjoin it to R. This is also a subring as well. Let's do an example where we actually have to check the conditions and not just, well, state that they're subrings. Consider the ring Z adjoined the square root of 3, and we're going to forget about the fact that this is a ring, and we're going to show that this is a subring of R. So assuming R is a ring, show that some subset of R is a subring. So remember, Z adjoined square root of 3 has elements of the form A plus B square root of 3. Okay, so let's check the conditions. First of all, we need to check closure under addition. So A plus B square root of 3, this is one element. You add it with another element, C plus D square root of 3. This is A plus C, and then plus B plus D square root of 3 if you just rearrange things and factor things. This is an integer, and also B plus D is an integer. So the sum over here definitely lies inside of Z adjoined square root of 3. Next, we need to check that additive inverses are in there. So if you want the negative inside of the subring, so A plus B square root of 3, then this is just negative A minus B square root of 3. But obviously minus A and minus B, these are just, well, integers. So it holds that the additive inverse of any element is always inside of Z adjoined the square root of 3. Let's check closure under multiplication now. So 3. If we take two random elements of the ring, so A plus B root 3, multiplied by C plus D root 3, let's FOIL this and see what we get. So we have AC plus BC square root of 3 plus AD square root of 3 plus 3 times BD. Now I'm going to move things around a little bit. First of all, I'm going to have AC plus 3BD, and then I'm also going to factor out the root 3, and we're going to get BC plus AD square root of 3. Now AC plus 3BD, this is obviously an integer. Also BC plus AD is also an integer. So this element does indeed take on the form that's required. So it is still in the ring Z adjoined square root of 3. And finally, we just need to check that 1 is inside of this subset over here, but 1 we can just rewrite this as 1 plus 0 square root of 3. 1 is an integer, 0 is also an integer, so this 1 over here definitely lies inside of Z adjoined square root of 3. Because all 4 of these conditions here hold, We don't even need to check that z adjoins square root of 3 satisfies all of those 8 axioms, as well as the closure axioms. It's enough just to check these axioms, and all the other axioms are inherited from this parent ring R. So that's a subring there. Let's take a look at ring homomorphisms. So definition. Let R and S be two rings, and I'm actually going to use a bit of color here, and you'll see why later. Then a ring homomorphism is a map which I'll call phi that takes you from R to S, which satisfies the following. First of all, it must preserve the addition operation on both rings. So for all A and B inside of your domain ring R, it must hold that if you have phi of A plus B, then this is the same as phi of A plus phi of B. Now notice I used the red and the green plus over here. This red plus is actually the addition in R, whereas this green plus, that's the addition happening in S. Second of all, we have something very similar for multiplication as well. We have phi of A times B, that has to be equal to phi of A times phi of B. And finally, we need the following to hold. Phi of the multiplicative identity in R must be the multiplicative identity in the ring S. And the reason why we need this third axiom here is to avoid some degenerate cases, because if the multiplicative identity is sent to the additive identity, let's say, then actually everything must be mapped to the additive identity, so it's basically just a zero map, which isn't too interesting. Now, as for the first two conditions, what exactly are they trying to tell you over here? Well, imagine your two rings, R and S. The map phi that goes between them must have this special property, whereby if you have two elements in your ring R, it doesn't matter if you add them in the ring R first to get this yellow element, and then you send it over to S, or if you send both of these guys over to S first, and then you add these two guys together, it should give you the exact same elements no matter which route you take. And the same goes for multiplication. It doesn't matter if you multiply in R first, then send it over, or if you send both elements over, then multiply in S. The addition and multiplication operation is preserved when you send the elements in R over to S. Okay, so let's take a look at some examples. So I mentioned this homomorphism in the polynomials video. We're going to let R be a ring, and we're going to also let A be an element in this ring. Then the map, which I'm going to call EV at A, so evaluation at A, which takes a polynomial, R of X, and sends you to a ring element. And how do you define this? Well, if you take a polynomial P in this ring R of X, you send this guy to P evaluated at A. So this P over here, this is really the P as a function from R to R, and you're evaluating it at A. This is exactly just like how we discussed it in the polynomials video. This guy is a ring homomorphism. So let's make this, well, not just an example, let's make this an example. It's also a definition and also a proposition. It's like a 3-in-1. And we can give a rather simple proof of this guy. Let's check if it preserves addition. So let's take our map EVA, and let's act on the sum of two polynomials. Okay, so this is just these two polynomials here as functions, but you plug in the element A. But how are the sum of two polynomials defined? Well, this is defined pointwise, so it's P of A, and then plus a Q of A. But notice, P of A, that's just EV of A. And then similarly for Q of A, this is just EVA of Q. And you can write down basically the exact same thing for the product as well. So the product of two functions, you define it pointwise. So it's P of A, Q of A, but this is just EVA of P, and then EVA of Q. And finally, we just need to check that multiplicative identity is sent to multiplicative identity. So what's the multiplicative identity in the ring of polynomials? Well, it's just the one polynomial, so EV of the 1. That's exactly the 1 function evaluated at A, but the 1 function is always equal to 1, irrespective of which elements you plug in, so this is just going to give you 1, but that's exactly the 1 in your ring. So this is quite a nice ring homomorphism to have. Let's take a look at another example. We're going to let R be a ring, and we're going to define a map phi that takes you from Z into this ring R. And it turns out for this to be a homomorphism, it's actually a unique map. So assuming this phi is a homomorphism, then we must have that phi of 1, so this is the identity in Z, so it's the normal 1 we're used to. This has to be equal to the 1 in the ring R. Okay, so what would phi of 2 be equal to then? Well, it has to be equal to phi of 1 plus 1, but assuming phi is a ring homomorphism, we can split this up as phi of 1 plus phi of 1. But hang on a minute, phi of 1 plus phi of 1, that's exactly 1 in the ring, plus another 1 in the ring, but this is just 2 times this ring element of 1. So just be careful, just like I mentioned in the polynomials video, this is not the multiplication in R, This stands for the repeated addition. And you can continue with this, and you can show, by induction if you want to, that phi of n must be equal to n times 1 in the ring. And this map also preserves multiplication as well, because if you take phi of n times m, well, using this definition here, this must be equal to n times m times the identity in R. So this is repeated addition n times m times, and it can show that this is equal to repeated addition n times. You take this guy, and then you multiply by repeated addition m times. But this is just phi of n, and then phi of m. And if you can't quite see why this is true over here, well, if you consider the right-hand side, you have basically n ones here added together. And then you also have m1s in another bracket. So we have n and then m. And if you FOIL this out, you're going to get 1 times 1 everywhere, which is exactly 1. You're going to get 1 added together, well, nm times. But that's exactly n times m copies of 1 added together. So it turns out for any ring R, there always exists this homomorphism phi, which is also a unique homomorphism that takes you from the integers into that ring. Actually, if you know a bit of category theory, then Z is what's called the initial object in the category of rings as we've defined them, because we can always create this map into any ring. And another example, I'll leave this more as an exercise, is to show that the map phi that takes you from Z adjoin the square root of -5 into the field with 2 elements, where you define phi of a plus b square root of -5 to be equal to a plus b, but because we're working in F2, you probably want to take mod 2 here. This guy is a ring homomorphism. Okay, so to wrap up the video, let's define the kernel and the image of a ring homomorphism. Definition: let phi from 2 rings R to S be a ring homomorphism. Then we define the following 2 sets for now. The kernel of this homomorphism phi, that's defined to be the set of all elements R in your domain ring R, such that phi of R gives you the 0 in the target ring. So this is the additive identity. We also define the image of phi to be equal to the set of all elements in S that can be hit via the map phi. So it's phi of R such that R is an element of the domain ring R. So if you have 2 rings, R and S, and you have a map phi that goes between them, then the image of phi is where all the elements in R land in the set S, and you can show that the additive identity must be inside of this image as well, because 0 must be mapped to 0. Then the kernel is everything inside of R that gets mapped to that 0 there. So that's a picture of what's happening if you wanted one. Now just a warning about these 2 sets, so I'll put some exclamation mark here. In group theory, you know that the kernel of a group homomorphism is a subgroup, but for rings, a kernel of a ring homomorphism is not a subring. It's actually something a bit more, I guess, important than a subring. The kernel of phi is an example of an ideal. And we're going to start talking about ideals, not in the next video, but the one after that, where we start constructing quotient rings. The reason why kernel of phi is not a subring is because in order for kernel of phi to be a subring, then the multiplicative identity must be in the kernel. But if the multiplicative identity is in the kernel, then we have phi of 1 is equal to 0. But this is bad because phi of 1 needs to send you to 1. And the reason why this is bad is because if you have phi of any element A, well, any element A can be expressed by A times 1, but by the ring homomorphism property, you have that this is phi of A times phi of 1, but phi of 1, this guy is 0. So this is phi of A times 0, but that's exactly 0. So if 1 is in your kernel, then it's very bad. This wouldn't be a ring homomorphism at all. Actually, it's not from this point over here, because to have a ring homomorphism, the identity needs to be sent to the identity. However, the image of phi is a subring. So let's make this a bit of a proposition. Let's prove that. So we just need to check the 4 conditions, so let R and S be inside of the image. And because it's in the image, there exists A, B inside of the domain ring R, where phi of A equals R, and phi of B equals S. But now we want to show R plus S is inside of the image. So to do that, consider R plus S, but that's phi of A plus phi of B. Phi is a ring homomorphism, so we can write this as phi of A plus B. And well, because it's the image of some elements in your original ring, R plus S is inside of the image. You can do something similar with multiplication as well, so R times S, that has to be phi of A times phi of B, but this is just phi of A times B. So R times S is the image of some elements in your original ring. And also additive inverses are in there as well, because the minus of a ring element is just minus of phi of A, and this is just phi of minus A So minus r is also in the image. And finally, the identity must be in the image as well, because by the definition of ring homomorphism, identities must be mapped to identities. So the identity is already the image of some elements. Okay, so that's going to be all for this video on subrings, as well as ring homomorphisms. So in the next video, we're going to talk a little bit more about ring homomorphisms as well as ring isomorphisms. And then from there, we're going to start taking a look at ideals and then constructing quotient rings and talking about the first isomorphism theorem. So very cool things coming up. So I hope you guys enjoyed this video, and I'll see you in the next one.